Elijah Gray. So Elijah Gray was an engineer. Because he was experimenting with electrical devices, he was known for creating a telephone prototype in 1876 in Highland Park. His idea was stolen from Alexander Graham Bell. Now, many people know Alexander Graham Bell as the inventor of the telephone. So, who copied the idea by writing it down in his notebook, which was the liquid transmitter for the phone. So, I think he took part of his idea. Bell did this because his family, mother and wife were deaf, and which led him to do this as he was interested in science of sound. Gray also made a musical telephone, which was the first electronic musical instrument. Handwriting that can go through a telephone system. Soon, Elijah Gray mentioned was then being used by banks to sign documents at a distance. So you could like write something down and then it could get transported. So Elijah Gray, like it sounds like this is one of those ones like, is it a stolen idea or not? It's like if you steal part of someone's idea, I'm not sure whether or not that counts as being a stolen idea. It depends, I guess, how much you use that idea that was stolen. That was borrowed from someone else, and it's definitely a bit of a gray area here. So the reason I picked Elijah Gray as one of the people to look at is because, yeah, some people, you could very easily say, oh, Elijah Gray had the idea of the telephone stolen, and like if that was the contention that you wanted to say, then I would say, yep, sure, there is arguments against that. If you wanted to say instead, no, his idea wasn't stolen. Part of his idea was improved by Bell. Be like, yeah, no, that's true too. It's like Bell didn't steal all of the idea. But the good news for Elijah is it sounds like he did invent something afterwards. So being able to send images over phone lines, which was in 1876 is pretty impressive, is a good sort of improvement. Like he actually did produce something, so he can be at least remembered for that. But I thought it was an interesting person to look at. Today's lesson, we're going to start talking about kinematic laws. Now, there are 5 kinematic laws, and you don't need to memorize them, but I will get you guys to write them down. And these 5 laws, what we're going to do, the best way to do them is a lot of practice. So what we're going to do with these 5 laws is probably today I'll teach them to you, and I'll go through one example. I think maybe on Friday I'll go through another example. Plus, I'll also give you guys I'll probably make the attendance question one of these examples. So I'll give you guys maybe a little bit of time at the start of the lesson to work on it, on the attendance question, because it'll be a bit of a challenge. Friday, so yeah, sorry, Thursday. I got that wrong. And then next week, next Tuesday, I'm going to go through this. I'm going to go through some of the harder questions and then give you guys some time. Wednesday, by the way, I'm going to let you guys know I probably won't be teaching on Wednesday. I probably won't be here next week because I'm probably going to be taking my professional practice day, which also happens to line up with my birthday, which is for no reason whatsoever, has absolutely nothing to do with me wanting to take a day off. But yeah, I'm probably going to organize that, but you guys will have motion 3 to work on, and probably is also motion 4 to start on, but I'll get you guys information on that next time. Before we do that, let's talk about what we did last lesson. Last time I took you guys through velocity acceleration. So we actually targeted these next 2, and we actually had already been talking about velocity. But what we did was we talked about what average speed means. So now it's total distance divided by total time. We did an example. And then we looked at instantaneous speed. What is instantaneous speed? And we looked at that. And then we did some examples of near and far away. And then we looked at velocity time graphs. Only for us to finish up on acceleration. Now, acceleration is a change in speed over a change in time. We looked at the equation. We said if the acceleration is in the same direction as the velocity, what it will do is it'll add to that velocity and make it go faster. If the acceleration is in the opposite direction of your velocity, it will instead slow it down, and it will subtract from that velocity and slow it down. It can actually subtract from the velocity so much that it makes it go backwards as well, but something worth knowing. And then we did two examples, quickly rearranging that formula that I showed you. And then we talked about accelerometers and where they can be used in engineering. So let's talk about our first kinematic law. Now, the kinematic laws are just ways of writing down, they're just ways of writing down laws that we've already been using. For example, and they all use no force. So they're calculations, equations that don't use force. They use constant acceleration. So that means if you're traveling at 2 meters per second squared, the whole time you'll be traveling at 2 meters per second squared. So let's look at an example of a kinematic law. We're actually going to take change in velocity. Change in velocity is acceleration times time, which is going to be your final velocity equals your initial velocity plus your change velocity. So this law here, your final velocity is equal to your initial velocity plus your change velocity. And change velocity is AT. This is the first kinematic law. Now you could actually create this law by also doing it a different way. I'm going to give you guys a second to copy this down, but then I'm going to show you a little bit of a different way that we could calculate this law. I'm going to give you guys about 30 seconds from now, and then I'm going to show you. That was a good coffee. Well, actually, it wasn't the best coffee in the world. I've had better coffee, but you know, I complain. What I want to show you is this law, V equals U plus AT, guess what? Can be found out in a different way. I've just shown you that way, but there's actually a better way to do it. Let me get ready to show you. And the way that we can calculate it is a lot easier because we're going to use the way that we just did no more than a fraction of a second ago. What was that method that we used a fraction of a second ago? The method was acceleration equals V minus U over T. So the final speed minus the initial speed gives you the change in speed or change in velocity over time. So therefore, multiplying both sides by T again, AT equals V minus U. But add U to both sides this time. V equals U plus AT. Same law. This is what we refer to as the first kinematic law. And it's the first of 5 kinematic laws. Now, each of the laws could be derived using this sort of method. I could then substitute a different value in there. I could substitute a value for speed as being distance over time and then change this completely. And then that would give me a new formula. And so I could rearrange these. But what I'm not going to do that with you guys. If there are any massive nerds here, and I know that there are some massive nerds here, you guys can actually derive each of the 5 kinematic laws using this idea of acceleration and this idea of, I guess, velocity equals displacement over time. Using those laws, you can rearrange them to get these 5 kinematic laws. But I'm going to show you what those 5 kinematic laws are now. Those 5 kinematic laws include right here. V equals U plus AT. X, remember X is the displacement, equals half U plus V multiplied by T. X equals UT plus half AT squared. X equals VT minus half AT squared. And V squared equals U squared plus 2AX. I have done these equations so many times that I pretty much have memorized them. But and I always forget the second one. To be honest with you, I don't use the second one very often, so I always forget it. But and I also find that these two here are very similar in my opinion. This is UT plus half AT squared, whereas this is VT minus half AT squared. So one of them is, the U one is initial velocity times time added, and then final velocity times time. If you've forgotten, by the way, I'll get you guys to copy this down. If you have forgotten what the symbols are, just so you know, X is displacement. So copying these down. You may want to, if you are a organized person, you may want to highlight these into your books or do some kind of either highlight them or maybe underline them or put a red box around them, whatever. X is displacement, U is initial velocity, oh my god, I wish I had my pencil. V is final velocity. I'm mostly doing this to give you guys a chance to copy these down. A is acceleration. And T is time. Now these rules actually make some questions a lot easier. These rules are not ones that were taught at Year 10 Science. I actually had a couple of students who did engineering maths term 1, whoopsies, and then they went to term 1 and term 2, and then they had their motion test, and they kept trying to use these, and the teacher, which was Mr. Dallas, kept saying, guys, don't stress. You don't have to know these complicated formulas. But because they kept trying to apply it, and it was my favorite thing was they kept trying to ask him complicated questions. It's like, guys, I'm just a simple science teacher, not a maths, not an engineering physics teacher. So yeah. Now you might be asking yourself, I doubt it, but it is possible. You might be thinking, holy crap, there are so many like equations. Normally, you usually get given one equation, you know, change in distance over time, or you'll be given a squared, c squared equals a squared plus b squared, you know. But there are 5. V equals final velocity, someone asked. Yeah, I can't write it. That's why I probably can't read it. V is final velocity. Oops, that wasn't supposed to be. Oh crap! I accidentally sent that to a private message to a random student. Okay. So yeah. So why there are 5 equations? Why do we need so many equations? Okay. So notice how there are 1, 2, 3, 4, 5 symbols. Can I ask you guys? I want you guys to do this. Tell me. I'm going to maybe do this in blue. I want you to look at that very first equation, the very first one that we did. V equals U plus AT. Now, given that there are 5 symbols here, can you guys tell me what symbol is missing from this first equation? What symbol isn't represented? You can either write in the chat or you can say it out loud. Which symbol is missing?
X.
X. X is missing from this first one. What about the second one?
A.
A. There is no A in this equation. What about the third one?
V.
V. There is no V in this equation. What about the fourth one?
U.
U. There's no U in this one either. The last one, sorry, what's missing in the last one?
T.
T. We're missing T in this last one. And then you can look and you can say, hey, these are all the letters. So in each one of these equations, you have 4 out of the 5 letters. And that's going to be really important because ultimately what that means is that you only ever need 3 quantities to find a fourth one. So how I usually write this down is I'm usually like, oh, well, those are the missing letters. And so what I would like you guys to do, is I thought this was on the slide. Could I get you to write down missing letters and just put these symbols next to each one? We're not probably going to use them, but it's just important to understand this is why we need to have 5 of these equations so that we can tackle, because then what that means is that you just go, okay, I've got 4 of the symbols, but I'm missing A, so that means I'm going to use the second equation down. And maybe you've got U, V, and T, and you need to calculate X, well, then you've got the answer in front of you. So just jot down that, add it to the list as well, maybe on the right-hand side. But yeah, that's why we need 5 of these equations. It's a bit overkill, but it's still going to be useful. Okay, time check. What have we got? We've got 11:33. So we've got about 20 minutes left. So there's probably enough time to maybe do 1, maybe 2 of the examples. I'm going to give it a go. But yeah, we're going to start using these equations. We're just going to start using them like we would any other equation. Now, to do these types of questions, there are some steps that we need to do. Perhaps the most important step is going to be for you guys is learning how to extract information. Because ultimately, most of you guys are pretty good with numbers, you're pretty good with maths. So I don't really need to teach you guys how to do the maths. It's just going to be about extracting the information. And the second hardest skill, and I'm going to try and go over it many, many times, is choosing the right equation. Ultimately, all of engineering, all of physics, and a fair chunk of maths is just knowing which equation to use. And if you know which equation to use, the maths is usually pretty easy. What I'm going to get you guys to do is we're going to do the very first example, which is question 1. You don't have to, by the way, guys, I put the laws that you just copied down. I've just moved them over here. You don't need to, obviously I'm not expecting you guys to copy them down again. The reason that they're over there is so that we can refer to them, we can look them up. But what we're going to do first is I'm going to get you guys to do this. Could I get you to write down this formula here? A car starts at rest at 20 meters. A car starts at rest, starting at rest, accelerates at 20 meters per second for 30 seconds. How far will the car go in that time? Jot that down, and then we're going to solve it. I'm asking you to jot it down because when I go to solve it, I'm going to do it on the paper, so you guys won't be able to see what I'm doing. Okay, let's start to do it. I've had enough time to write down the question, so I imagine you guys have had more. So let's tackle this question, explore what we need to do in order to solve it. Okay, so here's the question here. And the first thing I'm going to ask you guys to do, and this is the same thing that you guys should do in any kind of question, is can you guys tell me, I'm going to open up chat so I can actually see what you guys write, but can you guys tell me something that you think is important about this question? Something that you think is going to be useful in solving how to do this question here. There is an acceleration. Okay, so let's start with that. Okay, Oliver, you're going really quickly, but I love it. There's an acceleration. What is the acceleration? So there is an initial velocity. So let's start with either one of those. Let's start with acceleration. Can someone tell me what is the acceleration that they've asked for? Where does it say what it is? It's 20 meters per second. It's actually 20 meters per second squared, but you guys can't do that. So here is very first piece of information. Our acceleration is 20 meters per second squared. Now, this is something you should do with all types of questions. Is you should then say, well, how can I turn this 20 meters per second squared into another way? In other words, how can I extract that information? Now, in maths, what you'll usually do is you'll draw a diagram, and that's straight up what I think you should do. But in this question, when extracting the information, you're going to do it a bit differently to how you might do it in a maths question. What we're going to do is we're going to extract this 20 meters per second, and we're going to write it down here. How we're going to write that down is we're going to use a symbol. We're going to say A equals 20. In this case, we're going to say positive 20, just because it's accelerating. Now, what we've done now is we've taken that information, we've extracted it out. And yeah, as I said, if you were doing a picture and there were a Pythagoras question, they were saying, oh, a 10-meter ladder is leaning against the wall, you would draw an image of what you have. But this is the first step. This is the first problem-solving step you should do with any type of question. Try and rewrite the question in a different way. For us to rewrite this question, we're going to pull out the information. Now, someone said something else. What's another thing we can extract? You can pretty much steal Oliver's answer because he gave all of them. What's another thing we can just extract? What's the next thing we're going to pull out? Time. Let's pull out time. Thank you, Everest. I know that, yeah. So time is 30 seconds. What symbol are we going to give for time? T. T equals 30. So now we've extracted that piece of information. Is there any other useful information that we could probably extract from this question? You had one before that I ignored, but what's the other one? It starts at rest. Now this is actually one of the hardest things to pick up. The car starts at rest. Starts from rest. That means our initial speed, which the symbol for does anyone remember what the symbol for initial speed is? U. So that means our initial speed is 0, because that's what starts from rest. Now, whenever you see the word starts from rest, or comes to a complete stop, or starts moving from not moving, it means that u is 0 or v is 0. If you've got an object that stops moving, your final velocity is 0. Now they won't always tell you. That. Sometimes you'll have to figure it out. So that's one of the ones that makes it a bit hard. The last thing here is, what are we trying to figure out? What are we trying to calculate? What are we trying to figure out in this question? Guys, what are we trying to calculate?
Displacement.
Displacement, yeah. How far the car will go. We want to know what our displacement is. So we want to know what our value x is. Now the reason I switched to green, this is actually a technique that I stole from. I'm not sure if you guys remember, because he left the school last year, but Mr. Dong used to show me this one. He's like, you should always highlight your work, like the question, in a different color. The reason for that is then we can go back and we can check it. So what we've done now is we've gone through this and we've extracted all the relevant information. We don't care if it's a car. How far it goes can be just symbolized in x. So sorry, my pen's frozen. My pen's frozen. Oh crap! It's 11:40. All right, we've got not much time. We're going to get through this question, and that's going to be about it. Here we go. So now the next step is to choose an equation. So now let's go through how I would choose an equation. Well, I would look at the first one. So V, U, A, and T. Okay, so we haven't got a V, so we're not going to use this one here. Okay, so then we go to the next one. X equals half U plus V. Again, we don't have V, so we can't use this one. X equals UT plus half AT squared. UT, this one looks like the one that we're going to use. Because we've got it, this is the one that is missing V. If you remember this is the one that misses V, then that will help you know which one to use. So that's how we go through it. I sometimes just go down the whole list and go, oh, I'm going to use this one, I'm going to use this one. And sometimes you'll start to pick up a habit for it. You'll start to realize, oh, these two are good if you're missing U or V, and these ones are good for everything else. But yeah, you just go down the list and say, I can't use this one, don't have V. Can't use this one, don't have V. I can't use this one because I've got everything in there. So then what I do is I write down the equation. X equals UT plus half AT squared. Then I ask myself the third question. So the first thing we did was we extracted the information. Second thing we did was we chose a formula. The third thing we do is we ask ourselves, do we need to rearrange? And so I'm going to ask you guys, do I need to rearrange this equation, or does this calculate the term that we want to figure out? Do I need to rearrange it? No, I don't. This is the first question, so it's going to be easier than other ones. But the answer is no, I don't need to rearrange it. I want to find out what x is, and x is the subject, so I don't need to rearrange it. The fourth one then is to substitute. So I write down x equals, instead of u, I write down 0. Instead of t, I write down 30. 0 times 30 plus a half times a, I write down 20, times t, which is in this case is 30 squared. And then the fifth and final step is to solve. Well, actually, no, it's not the final step. Really, the last step, step 6 down the bottom here, is to check. So we're going to substitute this in. 0 times 30 is going to cancel. That's going to make 0. So that's going to be x equals a half times 20 is 10. It's going to be 10 times 30 squared. 10 times 30 squared, or if you don't want to do that, just put everything in your calculator. I don't care. 10 times 30 squared equals 9,000 meters, because it's, yeah, and that's going to be 9 kilometers. But we don't need to write that. We can just write 9,000 meters. Now, the last thing would be to then go, okay, does this, is to check it, does this make sense? Well, this is a positive number, so that makes sense. Is it a large number? Yeah, that's a pretty large number, but then again, we've been accelerating at a pretty fast pace for a very long time. So that's for like 30 seconds. If you imagine 20 meters per second, after 1 second, you're going roughly about 20 meters per second is about 60 kilometers an hour. So after 2 seconds, you're going 120 kilometers an hour. So yeah, it makes sense. You're probably going to travel a pretty far distance in 30 seconds. So it's always good to check your answer. And this goes for these steps, by the way, go for most questions, whether it be a maths question or physics question or a science question. Check your answer. Does it make sense? I had a couple of students in my general maths class last lesson. I was going through their extended response tasks, and they kept saying, oh, we have a tank that starts off with negative 5,000 liters in it. And I'm like, guys, does that make sense? Can you have a tank with negative 5,000 liters? And they're like, well, that's what the answer said. I said, well, then you probably got the answer wrong. If it doesn't make sense, you probably made a mistake. And yeah, they had made a mistake. What they'd done is they factored something in wrong. They hadn't chosen the right points. And so therefore they got a negative answer. So if you get a negative answer, you should always go, does it make sense? In this case, it does make sense. That's how you do the first kinematic laws. We've got 4 more questions to do, but we're not going to do them today. We're going to do 1 tomorrow and then 2 on Tuesday. But I'm going to leave you guys there. What I might do is I might take a photo of this here and put this on the Google Classroom so that you guys can access this later on. But that's the end of the class. I want to thank you guys for listening to me, and I will let you guys go.